So, welcome to today's lecture. We will continue our discussion on the concept of sequences. So, if you recall, we had started looking at the notion of a sequence, the convergence of a sequence, and then we said the limit of a sequence is always unique. We gave examples of sequences which are convergent and which are not convergent. A non-convergent sequence is also said to be divergent. We continue our study. We also looked at last time the notion of boundedness of a sequence, namely all the terms of a sequence lie between two bounds. Okay. So, here is a theorem about convergence and boundedness. It says that every sequence A n which is convergent, it is also bounded. So, convergent implies it is bounded. So, boundedness is a necessary condition for a sequence to be convergent. Equivalently, one can say not bounded implies not convergent. So, this is a theorem in calculus. We will not be proving this theorem. So, we will assume the proof of this theorem. Those who are interested, as I said, can always refer to some book on calculus or look at the web course on calculus developed under NPTEL. So, a sequence is convergent, then it is bounded. So, the use of this kind of a theorem is that if a sequence is not bounded, it cannot be convergent. So, this is how necessary conditions are used. If a necessary condition is not satisfied, then it is not true that it should be convergent. So, however, keep in mind that boundedness alone is not enough to say the sequence is convergent. So, here is an example of a sequence which is bounded, but not convergent. So, this is minus 1 to the power n is a sequence which fluctuates between minus 1 to 1 and it is not convergent. So, let us look at some more theorems about convergence of sequences which help us to analyze the convergence of a sequence. These are theorems in calculus, but can be used, we will be using these theorems, and either you can treat it as a rule for analyzing convergence of a sequence, or you can, if you are very keen, as usual you can look at the proofs in the NPTEL web course. So, this says if a sequence A x n and y n are sequences such that x n converges to x and a sequence y n converges to y, then the following results hold. You can, given x n and y n, you can construct a new sequence called where each nth term of the new sequence is the sum of the nth term of x n and the nth term of y n. So, look at a new sequence whose nth term is x n plus y n, where x n is a sequence which is convergent and y n is a sequence which is convergent. Then it says then the following holds: the sequence x n plus y n is also convergent, and its result, the limit of x n plus y n is x plus y, and similarly you can have the difference of the two sequences. So, you can construct x n minus y n. So, limit of x n minus y n is same as limit of x n minus limit of y n. So, it just you can intuitively keep it as the limit of the sum of sequences is equal to sum of the limits of the corresponding sequences, and similarly for the difference of the two sequences. The next result says about the product. Given a sequence x n and given a sequence y n, the nth terms can be multiplied together to get the sequence x n y n. So, nth term of the new sequence is x n y n. So, if x n is convergent and if y n is convergent, then the sequence x n y n, the product is also convergent, and the limit is the product of the two limits. So, it says limit of the product is equal to product of the limits if the both the sequences x n and y n are convergent. And the next is, so we have looked at addition of sequences, subtraction of sequences, product. Next we want to look at the quotient of two sequences. Of course, x n over y n will not be defined if y n is equal to 0 somewhere. So, one has to put a extra condition that if the sequence y n is such that its limit y is not equal to 0, then the result says then for some stage onwards, for some n 1 natural number, y n will not be 0. That means, x n over y n is defined for all n bigger than or equal to n 1 from that stage onwards. So, we have a sequence x n over y n which starts with n 1 onwards. So, this sequence is convergent and its limit of x n over y n is equal to x over y. So, limit of the convergent sequences is equal to limit of the quotient of convergent sequences is the quotient of the limit, provided the quotient limit is not equal to 0. So, these are four basic results about the algebra of limits, because we are adding sequences, we are multiplying sequences, subtracting and then dividing sequences. So, basically says that the limiting operations preserves the algebra if appropriately defined. So, quotient for the quotient we need y not equal to 0. So, these results can be used to analyze convergence of sequences. So, there is another theorem which again will not be proving, we will be using it. It says the following: suppose you have got three sequences a n, b n and c n. So, there are three sequences with the properties that the sequence b n is in between a n and c n for every n. That means, all the terms of the sequence c n. It is not really required that all the terms from some stage onwards, if it is true, that is also good enough. One can forget a few first few terms of the sequence. So, we want a n less than or equal to b n less than or equal to c n. So, that is one condition, and this a n and c n both converge to the same limit, say L. Then the result says then the limit b n also exists, the b n is also convergent and is equal to L. So, basically what we are saying is that if the terms of a sequence are sandwiched between two convergent sequences and the convergence of a n and c n in which between which it is sandwiched is same, both a n and c n converge to L, then b n also will converge to M. This is known as the sandwich theorem, which is also quite useful. Again, we will not be proving this result. So, let us look at the example. For example, let us look at the sequence b n, which is sine. Sine is a trigonometric function. If you know it, very good. If you do not know it, I think you have a look at it in some school book, how the trigonometric functions are defined. So, we will not go into the definitions of trigonometric functions. Only for the sake of examples, we will basically sine of an angle theta is defined, and this for every theta, sin theta is between -1 and 1. So, this is basic property that we will be using. So, b n is a sequence which is defined as sin to the power 5 of n divided by n square. Now, since this sequence b n is it bounded, is it convergent? So, this is a question. To analyze its boundedness, let us look at the absolute value of b n. So, that will be equal to absolute value of sin 5 to the power n by n square. Since sin is bounded by -1 to 1, mod sin is bounded by 1. So, we will get that sin 5 n divided by n square, this absolute value of b n is always non-negative, absolute value is non-negative, is less than or equal to 1 over n square, which is less than or equal to 1 over n. So, which is less than 1. So, this is a bounded sequence, and since it is bounded between 0 and 1 over n and 1 over n converges to 0. So, this b n mod b n is in between 0 and 1 over n. So, by sandwich theorem we get that this also converges to 0. Now, sin this. So, there is the absolute value of b n which converges to 0, and it is again a easy result which will assume that if mod b n converges to 0, then b n also converges to 0. So, that will imply that. So, we have looked at some tools which help us to analyze convergence of sequences, namely algebra of limits and the notion of sandwich theorem. Here are some more concepts about sequences which are very useful and important. So, we say a sequence A n is monotonically increasing if A n plus 1 is bigger than A n for every n. That means, every term A n plus 1 is bigger than the previous term, that is A n. So, as n increases, your values of your sequence keep on increasing. Keep in mind, we are saying bigger than or equal to, we are not saying strictly bigger, right. So, if it is equal, it will be okay for saying the sequence is monotonically increasing. So, we want for every n, the next term, that is A n plus 1, is bigger than or equal to the previous term, that is A n. So, then it is, we say it is a monotonically increasing sequence. Similarly, we will say a sequence is monotonically decreasing if A n plus 1 is less than or equal to A n. That means, as n increases, the values of A n decrease, right. A n plus 1 is less than or equal to. Again, we are saying less than or equal to, we are not saying strictly less than. So, the next term is at the most the previous one, it could be smaller. So, that is called a monotonically decreasing. So, monotonically increasing and monotonically decreasing. If you want to say it is strictly bigger, if you want to have that condition, then we will say it is strictly monotonically increasing, and similarly we will say a sequence is strictly monotonically decreasing if A n plus 1 is strictly less than A n or all n bigger than n. So, for example, if we look at the sequence 2 n, it is strictly monotonically increasing because the first term is 2, the second term is 4, the next term is 6 and so on. So, as n increases, the values of A n strictly increase. Yes, it is monotonically increasing. Is it bounded above? No, it is not bounded above, because for n sufficiently large, you can make 2 n as large as you want. So, it keeps on increasing. It is a sequence which is monotonically increasing, and it is not bounded above. Of course, it is bounded below, there all the terms are non-negative. So, it is not bounded above. Let us look at the sequence 1 over n. We have already analyzed the sequence. First term is 1, second term is 1 by 2, third is 1 by 3, fourth is 1 by 4 and so on. So, it is a monotonically decreasing sequence which is bounded above by 1 and bounded below by 0. So, this is a monotonically increasing sequence, monotonically decreasing sequence, and it is bounded above as well as below. Let us look at the sequence minus 1 to the power n. So, what are the terms of the sequence? We have seen it is a fluctuating sequence. It is neither increasing nor decreasing, because the first term is minus 1, second term is 1, third term is minus 1, fourth term is plus 1 and so on. So, it is a bounded sequence, but it is not monotonically increasing nor it is monotonically decreasing. So, it is a sequence which is bounded, but not increasing, not decreasing. The obvious simple fact is that if a sequence A n is monotonically increasing, then negatives of those terms of the sequence will be monotonically decreasing and conversely. So, a sequence is monotonically decreasing if and only if minus of A n's, they will be monotonically increasing, and vice versa. You can also say that a sequence is monotonically increasing if and only if minus A n's is monotonically decreasing. So, this is one way of going from increasing to decreasing or decreasing to increasing. So, here is an important property of real numbers, which we said we will state at an appropriate stage. So, we can now state the property of real numbers, that every monotonically increasing sequence of real numbers, one should specify that every monotonically increasing sequence of real numbers which is bounded above will always be convergent. So, this is a property of real numbers. You can take it an axiom for real numbers, and when one constructs real numbers from the rational numbers, this property automatically comes in. So, this is what is called the completeness property of real numbers. It is a very important property, and an equivalent way of saying the same property would be in terms of decreasing sequences. Every monotonically decreasing sequence of real numbers which is bounded below is also convergent. This property is not always true for sequences of rational numbers. One can have a sequence of rational numbers which is monotonically increasing and bounded above, but it will not converge to a rational number. So, in the domain of rational numbers, this property is not true. This property is true for, that was actually one of the reasons why one wanted to enlarge the collection of rational numbers to a bigger class of real numbers. So, real numbers have that property that every monotonically increasing sequence of real numbers which is bounded above is convergent, and every monotonically decreasing sequence of real numbers which is bounded below is also convergent. Some of the applications of this property are the following. Will not be going into the proofs of those properties. Let us look at, let A n denote the area of 2n sided regular polygon inscribed in the unit circle. So, you are given, so let us look at this property. You are given a unit circle. Unit circle means what? You are given a circle of radius 1. So, this is a unit circle. Its radius is 1. This is 1 unit. One would like to find out what is the area of the unit circle. Normally, in your schools, school books, one assumes the fact that area of the unit circle is a number called pi. Here is a precise definition of that using the completeness property. Let us try to estimate the area of the unit circle. To estimate this, what we will do is, let us inscribe inside this unit circle a square. So, this is a square, say A, B, C, A, D. So, it is a regular four-sided figure inscribed inside the circle. So, if I look at the area of the circle of the square, that we can find out, because we know this side is 1, this side is 1. So, I can find out the area of these 4 triangles using the formula half base into height. So, area of the four-sided polygon, regular polygon inscribed in the circle is known. Now, let us increase this value. Let us take the midpoints of these arcs and join these points. So, we are joined. So, now look at, let us call these points as P, Q, R and S. So, if I look at the polygon A, P, B, Q, C, R, D, S, A, that is the 8-sided polygon inscribed inside the square, inside the circle of radius 1. So, earlier the area of the square filled up a part of the circle. Now, we added these triangles, these 4 triangles. So, the octagon now fills more part of the circle than compared to the square, and the area of this octagon is quite easy to find because this side is 1. So, half base into height, again we can find out this area. So, what we are saying is, if we write A n equal to the area of the 2n sided regular polygon inscribed in C, C is the circle, then this A n is a sequence of numbers, and quite clear that A n is monotonically increasing. So, that means A n plus 1 is strictly bigger than A n. So, this is a monotonically increasing sequence of areas, and from the figure it's quite clear that if I keep on increasing the number of sides, I will slowly and slowly fill up the unit circle. Okay. And it is also obvious that if I look at the square outside, then the areas of all these 2n-sided regular polygons inscribed, they are increasing, but they never go outside the area of the circumscribed square. So, that means this is monotonically increasing and bounded above. So, implies by the completeness property of real numbers that limit n going to infinity a n will exist, and this limit one defines pi to be the number which is this limit. So, this is the rigorous definition of area of the unit circle, namely pi, as an application of the completeness property of real numbers. So, this is one of the applications of real numbers. So, if you take the regular 2n-sided regular polygons inscribed in the unit circle, then this is a monotonically increasing sequence which is bounded above and hence will converge. So, the limit is called denoted by the Greek letter pi, that is the area of the unit circle. This is one of the rigorous ways of defining area of the unit circle. Another application of the completeness property, how does one find square root of 2? Of course, you will say what is the point, we can always divide and then do it, right. But can we have a algorithm for finding this? Yes, there is possible. This was given by Isaac Newton, which said that let us start with the number x 0 equal to 1 and iteratively define x k plus 1 to be equal to 1 by 2 of half of x k plus 2 by x k. So, once x k is defined, x k plus 1 is defined, and one shows this sequence of real numbers is convergent using the completeness property, and the limit is nothing but limit exists, and that is what is called square root 2. So, here is another way of appreciating the concept of limit of a sequence is that square root 2, if you have seen earlier, we also mentioned that square root 2 is an irrational number. So, its value cannot be found exactly, like pi, the value of square root 2 cannot be found exactly. But since the sequence x k plus 1 or x k is coming closer and closer to this, so for large x k can be taken as a rational approximation for square root 2. And these are the approximations more often than not used in putting algorithms in the calculators and so on. So, this is a very practical application of convergence of a sequence of real numbers. So, we have looked at sequences of real numbers. We have looked at the limit of a sequence of real numbers and seen various ways of analyzing convergence and the completeness property of real numbers. Here are some important sequences which are useful. For example, if mod of x is less than 1, x is any real number with mod x and 1, then x to the power n. Of course, since mod x is less than 1, these powers will in some sense come closer and closer to 0, and one can prove that the limit exists. It is a monotonically decreasing sequence bounded below, and it converges, and actually it converges to 0. One can prove it rigorously using the tools we have described, but will not go into it. But we will use this because it is a useful limit for a number between, say, a positive number between 0 and 1. If you take its powers, they keep on decreasing and decrease to 0. For x greater than 1, here is another one. For x non-negative, if you take the nth root of x, that is x to the power 1 over n, like square root, cube root, there is nth root possible for real numbers. If you take this sequence, then intuitively one denominator n is going to infinity. So, 1 over n intuitively is going to 0. So, intuitively this limit should go to x to the power 0, that is 1. That is not a proof, that is only a way of guessing that this limit exists and is equal to 1, and can be proved rigorously. There are some more examples of this. For example, you have seen geometric progression in your school. If a n is equal to a plus a r plus a r n 1. So, there is a geometric progression with first term a and common ratio r. Then we know that the nth term can be expressed as a into 1 plus r to the power n divided by 1 minus r. And that is a simple fact that can be deduced. Now, if r is less than 1, say r is between 0 and 1, and I take the limit, this is going to go to 0. So, this says that limit of a n is a divided by 1 minus r, right, for r less than 1. If r is bigger than 1, this is going to keep on increasing. So, it is a unbounded sequence. The fact that limit of a n is a over 1 minus r, as if r is between 0 and 1, that is written as that we call this as a geometric series a plus a r plus dot 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 a raised to power n minus 1 plus so on. This is called a geometric series, is an infinite sum kind of sum there on the left hand side, and says this infinite sum actually exists and is equal to a over 1 minus r if r is between 0 and 1. So, this is a sum of a geometric series, which is once again an application of the fact that r to the power n when r is between 0 and 1 converges to 0. So, that is another way of looking at that. So, we conclude our lecture today for sequences by saying that sequences provide a intuitive tool for analyzing something happening at regular intervals at different time points, and helps us to analyze them. Eventually, when n becomes large, what happens to that? We will see applications of this in the lectures to come. Thank you.